It seems from 5A students, they are still having lesson for a while now before until they come. Now, maybe while we are waiting, you may read the topic on 34.8 about the thermochemical equations, and take a look on the enthalpy terms. We will call that standard enthalpy changes. And here comes quite a lot of the definition later on. Okay, so I would like to have your help by checking those definitions, starting from 39.10 standard enthalpy change of reaction, formation, combustion, okay, and neutralization. So you may find this, right, all those, and please find for me any common points while you talk about the term standard enthalpy change. Okay. I will give you about 3 minutes and take a look on that and try to see if you can manage. And try to figure out some way to have a better memorizing, right, of those definitions. As you all know, right, you need to have the memorization of the definition. Okay, for those students who have just entered the Google Classroom, I shall repeat the task. Now, you are going to study 34.8 thermochemical equations, standard enthalpy changes, and here comes 4 definition of different standard enthalpy change. Okay, please take a look on that and find me any common points while you memorize this, and can we generate some templates and try to find out what is the difference in between those 4 different definitions. Anyone who see 李澤星 and 黃奕朗? No, 李澤星and 黃奕朗, are you here? No. Now, we start to have a lesson right away. So last time we talked about the exothermic reaction and endothermic reaction yesterday. So today we would like to take a further look on those heat change at constant pressure, the enthalpy terms. So you may see certain notation while you do the calculations. So what is that? We will call that a thermochemical equation. Okay, thermochemical equation. Now, what is the difference between the balance equation and the thermochemical equation? Now, no much difference, isn't it, right? But you may see the enthalpy terms put here. Okay, the enthalpy terms put here. So what is that? It will tells you delta. First of all, the definition of the word delta H. delta H, we call that enthalpy change. Okay, enthalpy change. Now, which means that you are going to measure the difference between the enthalpy level of the reactant and product. So here comes that data. Okay, so you may have got that two scenario. One is the delta H pointing downward, the arrow of it, and the other one, the arrow of delta H pointing upward like this. Okay, so and also together with the sign of the delta H smaller than 0 and larger than 0. So take a look on that. If you say that it is minus, it carries a minus data. Okay, minus data. What does it tell about the reaction? We call it exothermic or endothermic. Do you know? Wang Zhenhei, what does the sign tell you? This reaction, is it exothermic or endothermic? Okay, okay, some students have said it is exothermic. So what is the in pictorial representation, which means that you've got the enthalpy level, we usually use abbreviation H to denote, while you have got these two. Okay, so we have got CH4 gas to oxygen gas to form CO2 gas plus 2H2O. While with the enthalpy level, enthalpy change being minus 890 kilojoule per mole. Can you see? Can you see that? It is just what you just see this. I can show it in pictorial representation like this. Do you understand? So we would call this a enthalpy change. Now it comes to our concern about the term, the unit. The unit for enthalpy change is kilojoule per mole. So what is the hidden message? Which means that for this reaction, okay, for this reaction, according to this equation, you may find 1 mole of methane burning with 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of water. Now it released 890 kilojoule of heat. Now take a look on the term. When I say the word released, you will directly denote with the sign minus. Can you see that? While for this, we don't have any sign. Can you see that? No sign for that, and we use that denote the sign, which means that heat is released. Now, this is a very important definition. I will draw your attention to this. I repeat, those, if you say that 890 kilojoule of heat are released for burning 1 mole of methane completely. And you will have delta H equals minus 890 kilojoule per mole. Now, and because the physical state of the reactants and the product, they will also affect the enthalpy level. That means you must, can you see that? You must include the state symbols in the thermochemical equation. Now, so what is hidden message? If I have this one, change it to steam, okay, the gaseous state, this enthalpy level will not be the same. Now, what would you expect if I changed the enthalpy level? If I change the physical state of water, right, from liquid to gas, which means I turn to steam. What is the difference? What is the difference in this enthalpy level, enthalpy change, and what and also this level? Okay, the enthalpy level of the product. Can you guess? Can you guess? If I changed the physical state of water H2O from L to G, what what will be the change bring about when you talk about this level, the enthalpy level, higher or lower, and this one, this value?
When it changes to liquid, the value will be more negative. If it changes to gases, and then it will be less negative.
Less negative. Now, so in other words, if you write down the gaseous state of H2O, the enthalpy level here should be higher or lower? This.
For
this one.
Okay. For L, it would be lower. For gas, it would be higher.
Yeah. So in other words, you are going to put this gaseous state to here, right? For example, now I do not for the time being, I will not draw it in on scale, but you may get to know that if I write down G here, right, the enthalpy level of the whole thing will be raised. So what do scientists talk about the term delta H being less negative is this value. Okay, this value, the magnitude of the which shows the amount of heat released in the reaction will be smaller. So okay, so amount of heat released will be smaller. So we will call that the delta H will become less negative. Can you get my point? Heat released will be smaller, which means that delta H will become less negative. Can you get the point? Now, so what is the meaning about that? It seems that you are going to raise the enthalpy level from when you have a change of state. Okay, it does make sense that the higher the temperature, right? The enthalpy level, the energy content, right, of the chemical will be higher. So that's why we will say that the level of which correspond to steam will become higher. Now remember, you need to put the whole thing upward, but not just simply I put the steam upward and leaving CO2 at the same position. Because you talk about the enthalpy level of the products as a whole. When you compare with the enthalpy level of the reactants as a whole, okay, we will take a look in the cluster. Because while you talk about the reaction, we will talk about those two chemicals must be present at that condition. So of course, if you measure the enthalpy level, if you're going to talk about their own relative level, enthalpy level, they are now at the same level. Can you get my point? So this is what you may know about this. Because of that, remember the stick when we write down the thermochemical equation. First of all, you need to show me enthalpy change for the reaction. With the sign plus or minus, okay? And second is the term or the equations, okay? Once you balance it, it agrees with that listed in the equation. And three is on the stick symbol. The stick symbol should be must be there such that it can truly reflect the enthalpy change of reaction. The change in state of any reactants or products will greatly affect their own enthalpy level, thus in turns affects the delta H value. Do you understand? So what is the hidden message if you want to talk about the burning of hydrogen in with oxygen to form liquid water and also for steam? Okay, even though I list it as 1 mole of hydrogen, 0.5 mole of O2 to form 1 mole of water and steam respectively. Okay, you may have the difference in the enthalpy level, okay, of the steam as said before. If you want to talk about these two, this one it is more unstable, and this one it is stable because I raise the enthalpy. I increase temperature, so I absorb much energy content, so the enthalpy level of steam is higher. So you may find that two data. Can you get the point? So what is the difference? Now, the difference of these two data, it is just the amount of heat released when you talk about 1 mole of steam turned back or 1 mole of water. So what is the difference? What is the difference? About 44, isn't it? 44. So if you write down this, you can also have the enthalpy terms, which tells you the change in state being minus 44 kilojoule per mole. Now, which means that if I have 1 mole of steam, I turn back to 1 mole of water, it releases 44 kilojoule of heat. Now, you can think it in another way around. Mr. Chin, what will happen if I talk about the reaction? It's not reaction. If we change the physical state from water to steam. Now you talk about 1 mole of water turn to 1 mole of steam. Of course, I need heat, right? So how much heat is needed? The answer is 44 kilojoule. Do you understand? You can think it backward and do the same thing to tell. So this is how we study the enthalpy level diagram or the thermochemical equation. Now, it is very interesting to see that if you write the equations as reverse, okay, we can also express the delta H value. But the change is that there is a change of sign, right? Plus to minus. So it seems like the change of state from gas to liquid, liquid to water, for water, the steam to water, water to steam. Okay, very similar, but it doesn't tell anything whether or not that is the reaction which is said to be feasible. Okay, so what is the hidden message? We can show it as calcium carbonate to form calcium oxide plus CO2, calcium oxide plus CO2 to form calcium carbonate. But later on, you may see some equations very strange in which, even though I write in reverse, even though I know in reality that you will not proceed, we can still draw it like this. So it is what we talk about the calculations of the enthalpy change. That is the characteristics of that. So theoretically, from the data, I will know this, but it doesn't tell you whether or not the reaction can go or not in practice. Okay, they just tell you the difference in the enthalpy level between the two. So what is a hidden message? You are going to the two equation having the same magnitude, but the sign is different. Okay, the magnitude is the same, but the sign I change it to positive to negative data. So if you're going to write the two equations in reverse. Okay, is that clear? So let's have a brief summary of what we have mentioned about the enthalpy changes. Now, you would talk about the state, you would talk about physical state, you talk about the magnitude of this, right? The larger the magnitude, which means that the difference in the heat content will be larger. In consideration of a sign, right, you may know that the reaction gives out heat or absorbs heat. Okay, with interaction with the surroundings. Okay, because for these, different people will have different measurement of enthalpy changes. So it's time to make it a standard. Okay, so here comes then the enthalpy changes. So we would measure the enthalpy changes in standard state. Can you see that standard state? Now with the abbreviation delta H, okay, with the sign here. Okay, with a sign here. So which, if you write down this, which means that you are going to measure at standard condition. Now, so let's take a look at what is meant by standard conditions. First of all, about the temperature being 290 Kelvin, which is 25 degrees, and a pressure is at 1 atm, atmospheric pressure. If you want to talk about the substances, is the standard state, okay? So which means that the most stable physical state at 290 Kelvin and 1 atm. Now, for example, if you want to talk about phosphorus and also carbon in terms of graphite or diamond, okay, it will have a definition, which one is a standard state. And all solution, and if you want to talk about the solution at the concentration being 1 molar, okay, being 1 molar. So let's have a look on this while you take a look on the on different definition of terms. So once I would write down the standard, okay, that symbol represent the standard. If you write down like this, we will call that a standard enthalpy change of reaction. Now take a look on that. So what does it mean by that? It tells you the enthalpy change when the molar quantities of the reactants, the products they are stated, and they will try the reactants that are stated in the equation to react together under standard conditions to give product. So which means that if you write down this, which means that 1 mole of ammonia of nitrogen react with 3 moles of hydrogen to form 2 moles of ammonia gas as standard conditions. It will give out, they will release 92 kilojoule of heat. Okay, now as said before, if you see the sign negative value, which means that heat is released. While you will also see an occasion where it is plus, which means that heat is absorbed, okay, from the surrounding. Can you see that? Taken in, release, it is different. If you see the word sign, it tells you difference in meaning. Is that clear? Now, if you write down the equation like this, this is rather problematic. I'll take a look on that too. So if you write down 2 mole of ammonia to be formed, you may have division, right? As 1 mole, how about 1 mole of ammonia to be formed? Of course, less heat will be released. So in what content are half of that? So you may see the delta H value being chopped from minus 92 to minus 46 kilojoule per mole. So you will see that the data should agree with the molar quantities as stated into the thermochemical equation. And it's now you may feel a little bit uncomfortable because we usually would not write down the balanced chemical equations with showing the fractions, right? So it is not a simplest whole number ratio, isn't it? But in the enthalpy terms, conceptually, okay, because I just say that these so-called kilojoule per mole, it should go with the equation itself. So if you have a whole multiplication or division of the whole equation, right, the enthalpy terms will be adjusted accordingly. Do you understand? The enthalpy terms will be adjusted accordingly. Is that clear? Let me see. I can't find metal. I just closed my book. Now, so can you get my point? So it is minus 46 kilojoule per mole. Now, so remember, the enthalpy terms will have that very special significance while you take a look on the multiple or division of the whole equations. The enthalpy change, enthalpy terms will be enthalpy change will be adjusted, okay, accordingly. Any questions so far? So what will happen? So what is the hidden message? If you have 2 mole of nitrogen, we have with 6 mole of hydrogen gas to form 4 moles of NH3. gas. So what is the delta H of reaction, standard enthalpy change of reaction for this? Thousand.
將92乘翻2加10。
Oh, what is that? What's the data? Minus
負184
so yes,
kilojoule
right, kilojoule per mole. Okay, kilojoule per mole, which means that if you think of the whole combination, right, to react to form 4 moles of ammonia, and it will release more heat, okay, than the previous equation with a multiple of 2. Now, because for the previous equation, you talk about 2 moles of ammonia being formed. I changed to 4 mole. So of course, amount of heat released will be doubled. Do you understand? So we will call the delta H terms will become more negative. Can you get my point? Now, so remember, for those people who do not study physics, you may feel uncomfortable about the term more negative. What does it mean by that? More negative, you are going to think of two ways. First of all, positive, negative. What does it mean? Negative, which means heat released. But you will say that more negative, which means that the magnitude, the data itself is bigger, which means that the more heat is released. Can you get my point? More heat is released. We call it more negative. Now, so it is quite different from the number 9. While you talk about, for example, minus 10 degrees to minus 20 degrees, okay? If you talk about minus 20 degrees, you will tell that they will have a lower temperature, okay? And minus 10 degrees is higher temperature. So that concept is a little different, okay? Because the delta H is a vector term. You will know this term later. Have you heard about vector scalar in physics? Have you heard of that term? So it is different. Any questions so far? Now your turn. Now you take a look on these 4 enthalpy terms of standard enthalpy change of formation, standard enthalpy change of combustion, standard enthalpy change of neutralization. Can you see that? That 3. So what are the common points while you talk about the definition? Take a look on that. Formation, combustion, and neutralization. Any common points? Now I'll give you 1 minute to take a look again, and I would like, and for those who knows what are the common points while you talk about the definition, please put it in the chat box now. They are exothermic reactions. Somebody say all exothermic. I did not say anything about this for the time being, huh? What else? I would like to ask you guys the similarity of those 3 enthalpy terms. Somebody say that all those they are exothermic, which means that all 3 they carries negative data. Is it? So take a look on these. For example, page 18. How about this? Understand the condition. Somebody say so. What else? Now, so you may find the enthalpy change of something. So it will be usually referring to this enthalpy change of, now for example, formation of a substance is the enthalpy change when 1 mole of the substance is formed from its constituents. Okay, it's the constituent element in their standard states under standard condition. The standard enthalpy change, yes, of what? Of combustion. Is the enthalpy change when 1 mole of the substance is completely burned in oxygen under standard conditions. Can you see that? The third one, the standard enthalpy change of neutralization is the enthalpy change when 1 mole of water is formed from the reaction between acids and acid and an alkali under standard conditions. So what?
錢 Sir，
Yes.
我想問下咧，但係如果你即係佢用佢可以 form 咗，即係有一啲係有嗰啲 carbonate 嗰啲咧，咁但係佢唔係 neutralization 嚟喎，咁但係都係 1 mole of water， 咁呢個點樣？
So if you want to talk about carbonate with acid reaction to form salt, CO2 and H2O, like this, right?
Yes.
So for this reaction, just go back to the equation itself. Is it neutralization?
No.
No, but that which means that you did even though it gives a delta H value, we will not tell it as the standard enthalpy change of neutralization. Instead, we will call that a standard enthalpy change of a reaction. Okay, a very general term. So these three, what we will just see is something very, very specific. Okay, specifically talking about certain type of reaction. So which means that we have got the one general term, standard enthalpy change of reaction. Okay, this is a very general term. Very general term. Take a look on this term. It is of a substance. Okay, is the enthalpy change of enthalpy change when and the molar quantities of the reactants as stated in the equation would react together with to give products under standard conditions. So somebody would have spotted that whatever definition you're going to take, right? You may see the term under standard condition, right? Can you see that? Now, this is something very general. So you may find it agrees with the term standard, right? You may see the word standard, 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 okay? And all follow term standard. So that's why so you will say the enthalpy definition, right? So you will find this one is a definition. Can you see that? I would like to change a little bit such that you guys can keep track of what is that. Is what is the enthalpy change? Can you see that? Is the enthalpy change. Of course, once you talk about enthalpy change, right? Of course, you need to express the term like this: the enthalpy change at under standard condition. Now, this is somewhat very similar. Can you see that? So what is the difference in between? Can you spot the difference in between? Lei Chen, could you please read again and tell me what is the difference in between? Can you see that now? So what is the difference is inside this sentence, right? Can you see that? This sentence, so what is that? This sentence will tell you this should be in line with this statement's reaction. Formation of a substance, can you see that? And 1 mole of something is formed from this considering under standard state. And combustion. If you underline the term combustion, of course, you talk about the substance undergo burning. Okay, so the definition is set as the substance is completely burned. But you may see one more important term is the word 1 mole. Do you realize 1 mole? 1 mole of what? Now, please, except the first definition is somewhat general. Now, for the first statement, it tells you the molar quantities. Can you see the word molar quantities stated in the equation? So this is the definition, because you may see the equation not necessary to be one mole of the chemical, right? And if you want about a substance, the forming of substance, so you may see that 1 mole of substance is formed. If you talk about combustion, you go in reverse. You're going to talk about 1 mole substance is completely burnt. Do you realize? If you want to talk about the neutralization, we will target of 1 mole of the product water will be formed. So, which means that if you write down 1 mole, that is not necessarily to be the reactant. It can be product. Like for example, for this definition, you talk about 1 mole of the product is the substance is formed. Similar as neutralization, 1 mole of water is formed. But remember, you got stuck back to the definition neutralization. But for the combustion, that 1 mole of the chemical is the fuel, right? It's the reactant, which will undergo complete combustion. So by doing so, I hope that you guys would get to know how to memorize these 4 enthalpy terms. I mean it, okay? Because in the public exam, people would always be asked to give the definition, especially the later 3. So could you please take a picture of that? Keep this in your mind with great care about these 4 definitions. Any questions? Now, so go back to the question raised by Lei Chen. You just talk about carbonate with acid, right, to form salt, carbon dioxide, water. It doesn't fit the remaining 2nd, 3rd, and 4th definition, right? It's not a formation of a certain substance. It's not a combustion, it's not neutralization. So we can never represent this type of equation under these three definitions. Instead, I use this general one. Now, it brings to our concern how to define all those, right? Isn't it? So take a look on the, let's take a look on the definition one by one to take a glimpse on the details before we go to the exercise, okay? So here, so what's so special about the term is element in the standard state, right? So what's mean by that? It tells you the most stable form of the under standard state. If you talk about an element, okay, which is you need to memorize something. For example, carbon. It's not diamond, it's graphite. Huh? Somebody may be quite puzzled, right? Or maybe quite surprised to get to know this part. For carbon, the definition is graphite, not diamond. Now, even though you think that diamond is harder than graphite, so conceptually, while you talk about the enthalpy level of graphite, when you talk about it with diamond, okay, graphite is more stable. Very strange, isn't it? Right? So you are going to search on the web, enthalpy, all of you please mark down. What is the difference between the diamond and graphite in terms of the diamond and graphite? Take a look on the web. Standard enthalpy change of formation of diamond. You search it on the web. So what do you know? Can you search for me? The standard enthalpy change of diamond, graphite. Take a look on that. So what will you find about the data? Now, I'll give you some time to search for it for me now. Standard enthalpy change of formation of diamond. Can you see the word? Oh, 1.6863, right? With the delta formation, which means that we are now bringing the enthalpy level from graphite to diamond to higher. Okay, how about graphite? Can we have the standard enthalpy change of graphite? Now take a look. Oh, it's just 0. It's just 0. So what is the meaning about this? So what is the formation of standard enthalpy change for formation of graphite and diamond means? Do you understand? You understand? So which means that the delta H of formation, now I would like to use abbreviation here, right? Of C bracket graphite is 0 kilojoule per mole. Delta H of formation of C diamond is said to be plus 1. Is it 1.8? If I remember correctly. Yes, 1.8, 1.9, 1.863, 1.863 kilojoule per mole. So what is the significance of this? What is the meaning of this? Which means that you're talking about the equation, the transformation from C graphite to form C graphite. Now, why? Because it is the most stable state for carbon. So according to our definition, we would like to write this. How about this? Formation of diamond being this, which means that this is a transformation from C graphite to C diamond. So if you write down the enthalpy level diagrams, so you may find carbon, graphite, carbon, diamond, upward here, right? So delta H being plus 1.863 kilojoule per mole. Okay. While you become adults, you may have girlfriends with you. Okay. Instead of buying a diamond ring to her, you may choose to buy graphite. Tell him or tell her the concepts, right? Which one is more stable? It's not diamond. Graphite is more stable. Standard enthalpy change of formation can be negative or positive. Now, so it is not necessary to be negative. Okay, it can be negative, it can be positive. And you are going to express the standard enthalpy change of formation of methane as example. You may write down like this, or you can also write down like this. Now, this is the thermochemical equation. Remember, whenever you write down thermochemical equation, you need to show the equation as well as the delta H value together. If you use shorthand method, you need not show the equation. Instead, you write down delta H with the standard state with the middle bracket. Okay, with writing this. So what is the hidden message? If you write down this, can you write down the equation? Now, for example, I'll give you this one as example. You can write down this delta H formation of what? Methane being minus 74.8 kilojoule per mole. Okay, how about this? If you write down the ethanol, formation of ethanol, so what is the equation you're going to talk about? 1 mole of ethanol will be formed. Okay, from its constituent elements at its standard state. So which is graphite, hydrogen, and oxygen. Okay, and together with the delta H value of formation being minus 278 kilojoule per mole. Do you understand? So remember to balance the equation. We have got 2 graphite. How about how many hydrogen gas? There should be 6 on the product side, so it is 3. How about oxygen, O2? On the right hand side, it's just 1. So you write down this. To form 2 carbon, 6 hydrogen, and 1 O. Now, remember, it's not change, right, to have half mole of O2. Our focusing point is for per mole, right? Per mole of what? Formation of 1 mole, okay, of ethanol. So, although all other data should be adjusted to make sure that you write down in the equation 1 mole of ethanol. Is that clear? So for O2, it is forced to be written as half. Do you understand? So if you write down, so if we bring to our concern that why we say that C graphite is 0, right? Because for all elements if you write down elements, their standard enthalpy change of formation, it is just no change in the formation. So the delta H value for all elements as a standard state being 0 kilojoule per mole. Do you understand? Remember, delta H of formation is usually negative, but sometimes we have positive. So if you write down something as positive, which means that the product to be formed, it is less stable energetically. So you write down less energetically stable or energetically less stable. Is it is also okay? Okay, energetically less stable. So when you compare it with the constituent elements, do you understand? I do understand. Any questions so far? But you want to talk about combustion. The enthalpy level, it must be negative. Must be negative, okay? Because when you want to talk about burning, it is an exothermic process. So it is a difference lies on the magnitude, right, of the delta H of combustion. When is larger and smaller. So remember, if you write down this combustion per kilojoule per mole of what? Its time is graphite. So you may write down the abbreviation for this delta H C graphite. Remember, per mole means per mole of graphite. Now, similarly, while you write down kilojoule per mole for delta combustion for this equation, which means that you are going to show the combustion of 1 mole of what? CH18 liquid. Okay, do you understand? So remember, please keep track of the term per mole, and it should be go with the fuel to be burned. That's why for O2, as said before, please accept that the O2 is not necessary to have a stoichiometric coefficient be a whole number. It can be a fraction. But still balanced, okay? Can you see that the equation must be balanced, but the field should be make it as 1 mole. Now remember to show the 6 symbols. But somebody may also argue, Mr. Chin, can we also say this equation being delta H of formation of graphite? Carbon dioxide, sorry, carbon dioxide. Can we also say so? Now, because if you write down formation of carbon dioxide being minus 394 kilojoule per mole here, which means what? Per mole of carbon dioxide to be formed. So conceptually, you can also write like this. Do you understand? It's your turn. Excuse me. I'm sorry. Now take a look on class practice 34.5. And I'd like to check the answer after 2 minutes. I'll take a long time. I'm going to wash my hand first. Excuse me. All right, question 1A. Can I have Ho Hao-Yap? Could you please state the meaning of this term, standard enthalpy change of formation of heptane? So what is the meaning?
The standard enthalpy change of formation of heptane is the enthalpy change when one
is the enthalpy change when
1 mole of the heptane is formed from it
is formed from constituent
element in their standard stage under standard condition.
Okay, is the standard state under standard conditions. Correct. Okay, so it will be nice if somebody will write can show me the equations involved. Okay, thank you. Magalop, what is the equation involved if you write down this? Using heptane as an example. You write down the form 1 mole of heptane is formed, right? So where is it? Is it the reactant of the product side?
係咪 C 再加 CO2？ 我唔知。
C plus CO2. And then, so the whole equation is, now, so what is mean by 1 mole of heptane is formed? 1 mole of heptane is formed, which means that C7H16. Okay, it is written at the product side. So it is the only product in this equation. What is the physical state for heptane under standard conditions? Heptane. Solid, liquid, or gas?
Liquid.
Liquid, okay? Or more than 4 carbon, we will call it liquid, right? Usually, right? So, and you write down what is the reactants. So there should be 2 reactants which makes C7H16. All those reactants, they are element, okay? Constituent elements. So the answer should be carbon and hydrogen. Now remember, what you write should be at their standard states, okay? Under standard state. So hydrogen, the standard state should be H2 gas. How about carbon? What is the standard state?
Graphite solid.
Yes, it's a graphite solid. So you may write down solid graphite, or you simply write down it as graphite. So what is missing? It's the balance equation. So you write down 7 carbon graphite plus H hydrogen gas, H2. By doing so, you to form 1 mole of C7H16. By doing so, you may write down the 1 mole of heptane is formed. So that is the meaning. Questions? Any questions so far for that? Lam Seng-Han. Standard enthalpy change of combustion of heptane. So what is the definition?
Standard enthalpy change of combustion of a substance is the enthalpy change when 1 mole of the substance is completely burned in oxygen under standard conditions.
1 mole of substance is completely burned.
係 1 mole of heptane.
One mole of the substance is completely burned in oxygen.
Okay, 1 mole substance. So according to our example, I use heptane as example. So it is heptane. Okay, so one of heptane is completely burnt with oxygen. Now, usually oxygen should be in excess in practical sense, right? But once you write down the equation, you need to write as excess, right? With oxygen under standard conditions. So what is the equations involved? How will you express in the equations? How? Everyone
C H16加 O2
C7 H16 liquid O2 to form
CO2 and H2 and then balance.
yes, because yes, you're going to balance it. You are going to have carbon dioxide and water. So what is the stoichiometric coefficient? It must be one mole of heptane. How many moles of oxygen? There should be 7 CO2 or 8 H2O, leaving behind 14O plus 8O, 22 divided by 2, it is 11. 1, 11, 7, 8. Do you understand? So remember, this one must be 1. Now, by doing so, you can say that 1 mole of heptane is completely burnt. Now, remember, 1 mole of heptane, which means this one must be 1. This one must be 1. Understand? So how about the second questions? What is the standard enthalpy change of formation of NO2? NO2. So according to the definition, this is the standard enthalpy change of a 1 mole. The enthalpy change when 1 mole of NO2 is formed from its constituent elements in this standard state under standard conditions. So this equation, does it show the formation of 1 mole of NO2? No, I change a little bit.
Should be divided by 2, I think.
Yes, whole equations divided by 2, and this is the answer. It is plus 34 kilojoule per mole. Now, because you are talking about less NO2 to be formed, just half of them from the original equation. So of course, heat release with heat absorbed. Okay, heat absorbed from the surroundings will be less. Now remember, this one is endothermic, which means that heat is absorbed from the surroundings. Now, you may find it quite strange. Even though I call it is cold, it's cooler. Can you say that cool is given now? No. In physics, well, you usually express with the term heat. So you may either describe it heat is released or heat is absorbed, but not telling you that the cool air that comes to you absorb that cold, right? No such. Okay, it's quite different from Chinese saying, right? So in physics term, we call that heat is absorbed from the surroundings. Very strange, isn't it, right? Now, how about neutralization? For neutralization, you would have those enthalpy terms, right? No matter what acid and alkali we are having. So what are they in common? Can you see that? It is about minus 57 point something. Can you see that? No matter what combination of acid or alkali it should be. But of course, that saying it should go with the term here, underline that, strong acid, strong alkali. Second, the acid must be monobasic. So you may find this. Why is it like that? Because you are talking about the formation of water from this equation, hydrogen ion, hydroxide ion to form 1 mole of water. So because of that, once you write down the ionic equation, it's not surprising to see that the enthalpy changes of different combination of strong monobasic acid, strong alkaline, they are more or less similar. more or less the same. However, while you talk about weak acid or weak alkaline or both cases, this enthalpy change of neutralization will be smaller magnitude. Smaller the magnitude. So for example, if you take a look on this enthalpy change of neutralization of a weak acid, this one, all of you please mark it down. It's a weak acid with a strong alkali. Now, even though I mark it, this one is a monobasic acid, to form 1 mole of water, the heat release will become less. Why? Some energy is needed, right? To what?
Ionization.
Yeah, good. Ionization. So that's why we will bring to our concern that if you have different combination of acid and alkaline, which experience the difference in the change in delta T. Do you still remember? The temperature rise. I use different combination of acid and alkaline mixed together. We measure the temperature rise. But with different combinations, we will have different delta T. And also, it agrees with the number of moles of the water to be formed, whether or not the acid and alkaline combination is strong or weak, and also whether or not the acid is the basicity of the acid. All those other factors, they will affect the final delta T of the solution. So what will happen if I have finally this one? Now please check for me. Finally, before we end up the lecture today, so please finally check for me. If I have these, and also how does these 3 values will be different from this equation? And can you explain? So this is our task today. Okay, how does these data, the other 3 data, when you compare with the HCl plus NaOH to NaCl and H2O, how does it differ in the enthalpy terms when you talk about this with the other 3 equations, and give me the reasons. Is that clear? So this is what I would like to ask you guys to finish it and return to me today. This is your task. I would like to have a homework shortly, classwork shortly onto your Google Classroom. Please type for me for understanding about this. Now, so today we have covered mainly the enthalpy terms, standard enthalpy change of reaction, standard enthalpy change of formation, standard enthalpy change of combustion, standard enthalpy change of neutralization. So we try to tell you what is commonly shared is about under standard condition. Okay, so the standard condition is defined as 298 Kelvin, 25 degrees Celsius, atmospheric pressure being 1 atm. For a solution is 1 molar. While the substance is measured at the standard state. Well, here comes a different definition. The different definition, besides reaction, you may see the word 1 mole of something, right? You are going to stick back to the equation to figure out this. Now remember, what you write it doesn't tell the reaction can go. It is just according to the definition. Now, especially for formation, it's not say that we did not say that for the formation of a certain substance as written in this, in reality, we will have this. For example, if I produce NO gas, or can I have this formula, this combination of the chemical, it can produce NO? The answer is yes, or it can be no. Now, similarly, for the production of benzene, can we have 6 mole of carbon, 3 mole of hydrogen gas, and we can produce 1 mole of benzene? In reality, the answer is yes, or maybe no. I don't know. But in the practical sense, the answer is no. But we still have the enthalpy terms. Okay, is that clear? Okay, so we stop it here, and I would like to check your classwork today. Thank you. Bye-bye.